Now we're going to think about the bracket notation and how we use it to think about expansions on basis sets. Suppose the function is not represented directly in terms of a set of values for each point in space, but instead we've expanded it on a complete orthonormal basis. So this is a set of basis functions, psi n of x. And we've expanded it in the usual way. So here are our expansion coefficients times each of the basis functions. We've added up all of these, and that represents f of x. And we could also write the function as the ket that is simply this vector with each of these expansion coefficients. Now, let me say right away, you may think that somehow this is a different vector. The idea here is that this is the same vector in the space. So this ket vector is the same vector in the space, whether or not we write it this way, or whether or not we'd written it with all the values of the functions in here instead. Anyway, this is our ket vector now representing this function, written in this form now, and it may well have an infinite number of elements. And the bra vector would just be the complex conjugates of all of these expansion coefficients, now written out as a row vector. When we write this function in this different form, as a vector containing these expansion coefficients, we say we have changed the representation of the function, but the function is still the same. We're just representing it a different way. So the function f of x is still the same function we had before, and the vector is still the same vector in our space. What we've done, though, is by changing the representation, we've just changed the axes that we use to represent the function. So the vector is the same vector, it's just that the coordinate axes have changed. And now these coordinate axes have got these numbers are the projections onto the new axes. And these axes themselves that we're using are just the axes corresponding to those basis functions as vectors in the space. We'll look at that again later. So just as before, we could evaluate this integral here. We could work it out just using the values of the function at all the points, or we can expand these functions here. Expand f of x, this is the expansion of f of x, and we could similarly expand f star of x, the complex conjugate. We have to use a different index here in order to do this, of course. We just get the complex conjugate of the expansion coefficients and the complex conjugate of the function. So we can move the integral inside the summations here and move everything around. So we have these integrals inside here. Of course, these integrals are just giving us a Kronecker delta here because these are an orthonormal basis, we presume. So finally then, when we have the Kronecker delta in here, that means that this summation just turns into the summation of all of the modulus squared of the expansion coefficients. And of course, that's just the product of these two vectors, just as before. Now, we learned already that this integral here was just the sum of the squares of the expansion coefficients. We already knew that, and it didn't matter which way we worked this out. We get the same answer for this integral here, and the same is true here. It doesn't matter which way we wrote the ket and the bra vectors, whether in this representation or the other representation with the values of the functions in it. The inner product of the function with itself is just the same number. So though we've changed the representation, we've not changed the answer to this particular inner product of f with itself. The answer is the same no matter how we write it. Similarly, if we were to expand another function, g of x, on the same basis, now we'd get expansion coefficients, say dn instead of the cn, then this integral here would correspond to the product of these two vectors, the expansion coefficients for f and the complex conjugates of the expansion coefficients for g. And of course, that is just the bra-ket product here of the bra version of g and the ket version of f. Note that the result of a bra-ket expression like this, or this one here, is simply a number. In general, it's a complex number. This is certainly a complex number in general. And that's easy to think of if we think of this as a vector multiplication. Note this number is not changed as we change the representation, and that's a very important point. This is an inner product, and just like the dot product of two vectors is an inner product, it doesn't change if we change the coordinate system. And you may remember that about vector dot products. The dot product between two vectors is the same no matter what set of coordinate axes you use to represent it. And the same thing is happening here. These are the same ket and bra vectors here as we had before, no matter what representation we use for them. They're the same vectors in the space, and their inner product is the same. That's the way that we think about it. But we may have changed the representation, which is analogous to changing the coordinate system for thinking about two geometrical vectors. Now, we can continue to use this notation now to write down ways of thinking about expansion coefficients. So, in our expansion here of the function f of x on this basis psi n of x, with our expansion coefficient Cn, or the dn in this expansion of the function g of x, this is simple to evaluate these coefficients because, as we know, these functions are orthonormal, and we've done this before. Since psi n of x is just a function, we can also write it as a ket now, if we want to. And to evaluate this coefficient, for example, some specific coefficient Cm, all we do is we pre-multiply by the bra vector. So, pre-multiplying the ket vector f of x by the bra vector psi m of x, well, let's look at what that does. We'll put that inside the expansion now. Our expansion now, we're writing out the ket vector versions of psi n of x. We're pre-multiplying by the bra vector version of psi m of x. Of course, since this is an orthonormal set, these just reduce to Kronecker deltas, and so we have our expansion coefficient Cm. So our expansion coefficient Cm is simply this bra ket product. Using the bracket notation, we can write out this function as the expansion, as we talked about before. This is the expansion using the ket vector version. We can move this number around if we want to. Moving numbers and vectors, numbers commute with vectors, so we can move the number to here, and we can give our version of that number and get this rather intriguing looking notation here. This is also a way of writing the expansion of f of x, and we'll come back to see another way of interpreting what that means later on. As we said, because Cn is just a number, it can be moved about inside the product. Multiplication of vectors and numbers is commutative. Often in using bracket notation, we will drop the explicit argument x, in which case we can write out this slightly more compactly.
So now we see a key reason for introducing the Dirac bracket notation. It's a generalized shorthand way of writing the underlying linear algebra operations we need to perform. And it can be used whether we are thinking about representing functions as continuous functions in some space or as summations over basis sets. It will also continue to be useful as we consider other quantum mechanical attributes, ones that are not represented as functions in normal geometric space. One good example of that is the spin of an electron, though we will have to postpone the detailed discussion of that for some later time.
Now, in quantum mechanics, the function will often represent the state of the quantum mechanical system, such as the wave function, and the set of numbers represented by the bra or the ket vectors are also just representing this same state of the system. Hence, we refer to this ket vector here as the state vector of the system if it's in this state corresponding to that function f. And we could also refer to this bra vector as simply the Hermitian adjoint of that state vector. In quantum mechanics, the bra or the ket always represents either the quantum mechanical state of the system, such as a spatial wave function psi of x, or some state that, at least in principle, the system could be in. such as one of the basis states, psi n of x. Now, the convention for symbols in bra and ket vectors is really rather loose. Usually one deduces what is meant by what's inside the bra or ket based on the context that you're in. For example, if it's obvious what basis we're working with, then we might just simply write the ket vector as something with maybe an n in it to represent the nth basis function. It would just save us some writing just to put in n instead of saying psi n or something else more complicated. So we simplify this notation to this one, or maybe all the way down to this one here. Whatever we put inside the bra or ket should just be enough to make it clear what state we are discussing. Otherwise, there are actually really no rules for this notation. What's inside here is just a label that tells you what the state is. For example, we could write this expression, all of this entire sentence here, and put it inside a ket vector. There's nothing wrong with that mathematically. This statement in here is enough to tell you what this ket vector is representing. It's rather silly to write it out in this way, but this is perfectly legal mathematically. What's inside the ket vector is just a label that describes for you what the state is. But we probably already know that we're talking about a harmonic oscillator of some kind in the problem that we're dealing with, so we don't need to write all this out, and we might just simply write 0 because this would be the n equals 0 state of this harmonic oscillator. But as I said, there's no particular rules for what is inside the bra or ket vectors. They're just labels. So here we might have 0 representing this quantum number, and that would be quite a common notation, but it's not a defined notation that there's always that specific meaning in an arithmetic sense to what's inside the bra or ket vectors. Either of these is perfectly correct mathematically.
Note that because the convention for what we put inside these bra and ket vectors is very loose, essentially they are just labels that we like for whatever state we're describing, there is no particular reliable rule for manipulating anything based just on what is inside the bra or ket vectors. It could be that we used a wave function as the label, or maybe we used some quantum number, or maybe we have some other descriptive name. Unless we explicitly are attaching some direct algebraic or arithmetic meaning to the label, which we might well be doing if it's a quantum number, for example, we cannot reliably perform any particular mathematical manipulation based just on what is inside the bra or the ket. It is best to regard these labels as just being descriptive text, essentially, unless we know otherwise in a particular situation.